Hello, welcome. So today is a recording for Friday, February 17. Now, we'll see if we need this recording. I should, knock knock, be back tomorrow. Last night, well, that's all you need to know. So let's go ahead and get started. So we've done lots of things with quadratic inequalities, quadratic functions. We've talked about how to find their zeros. We've completed the square, which lets you do basically anything you would want with them. In particular, lets you graph them. What else have we done? We have talked about optimization, so we can find the maximum values that these things take. So we can answer the question, let's make it so the max exists, of that function. That's something we can do. So we can see how high the function gets. We can find that height. Today, we figure out how to solve that. So there's the line at y equals 1. We will discuss how to find that part of the parabola. And let's go ahead and build up to that with something of an application. Example, Dennis Mitchell has snuck into the backyard and Mr. Wilson is playing toss surreptitiously with a ball. Each toss imparts to the ball an initial velocity of 15 meters per second. Under that assumption, the flight of the ball is modeled by, and you know what I'm about to write down. There's the term that comes from gravity, -5 meters per second squared, t squared, plus something coming from the initial velocity, 15 meters per second, times t, h in meters, t in seconds. So we have a model. That's good. Let's finish the question. Mr. Wilson is inside on the second floor reading a newspaper. The moment that this ball exceeds a height of 7 meters, it will enter Mr. Wilson's field of vision. Here's the question then. For each toss, how long is the ball within Mr. Wilson's field of vision? So let's think about this, and let's start by writing an inequality. So let's write down this inequality. We want to know, so something bad happens when the ball exceeds a height of 7 meters. So it looks like we need to solve h of t strictly bigger than 7 meters. And we've already said the height's all measured in meters, but let's just be explicit, make sure that we're saying that the units are consistent. Cool. So let's solve that inequality. So here's the strategy I'll propose for solving almost any inequality, but in particular quadratic inequalities. Step 1, we will solve for equality. And if you like, this is saying, well, whatever the graph of this function looks like, time versus h, it'll look something like that. And so if there's a height of 7 meters, well, there's the bit of the graph which is above 7 meters. If we can find those two endpoints, then we'll be done, right? So let's just find those two endpoints. Well, what are those two endpoints? Those two endpoints are the solutions to h of t equals 7. So let's solve that. Let's solve -5 t squared plus 15t equals 7. That's not so bad. So let's follow the strategy of the quadratic formula. I think that means I should get everything onto the same side. Is that better? Nah, that's a little bit too harsh. Let's get everything onto the same side. And let's try to get everything onto the same side in a manner that minimizes the number of negative signs. So I guess it means I'll move everything to the right-hand side. So I'll rewrite that as 0 equals 5t squared minus 15t plus 7. And you could try doing this by factoring, but to do that, well, there are two things that make that complicated. The fact that both of those are not equal to 1 makes that unpleasant. Plus, they're both prime, so there aren't that many factors to walk with, so I don't think this will factor anyhow. Maybe I'll drop the following. No. So let's use the quadratic formula to do this. So by the quadratic formula, it looks like x is equal to negative b, so negative 15, also known as positive 15, plus or minus the square root of negative 15 squared, those parentheses matter, minus 4 times a times c all over 2a. All right, so there's a thing. Let's see what this becomes. There's spaces for on. All right, so that is 15, fine, plus or minus the square root of 15 squared, that's not so hard. 15 times 15, 5 times 5 is 25, carry the 2. $225 minus 4 times 5 times 7. Let's see, 4 times 5, that gives me a 20. 20 times 7 is what, 140? All over 10. All right, trucking along. 15 plus or minus the square root of, I can do the subtraction, I think. 5 minus 0 is 5. 12 minus 22 minus 14 is 8. 85 all over 10. All right, and 85 isn't a perfect square, but maybe it has a perfect square factor. Let's factor 85 and just see if it simplifies. So let's see, 85 is 5 multiplied by 13. No perfect square factors. There's no simplification to be done. So when does the ball enter or leave Mr. Wilson's field of vision? At these times, maybe we want decimal approximations too. So let's see, it looks like it enters in whichever of those times comes first. And you can look at this and tell. When you make the negative choice there, that'll be the lesser of the two. And let's maybe even check that that'll be positive. Root 85, 85 is pretty close to 84. 81 is the closest square. 85 is pretty close to 81. Square root of 81 is 9. So this number will be somewhere around 9-ish. And 15 minus 9, that's still positive. So it enters at 15 minus root 85 over 10 seconds, leaves at 15 plus root 85 over 10 seconds. Nice. So that's also told us something based on the graph of the function, but let's make sure that we have them in the right order. To confirm, let's pick a sample point between these two and see if it's actually in his field of vision. So here's a number that's between. If you subtract 85, oops, or you add 85, well, definitely if you just add nothing, that is somewhere between them. So sample time, 15 over 10 or 1.5 seconds. Let's see what happens. So -5 times 1.5 squared. Yeah, this is the right way to do it. Plus 15 times 1.5. Let's see what that works out to be. You could use a calculator for this, but maybe I'll stick with my stubborn approach of doing computations by hand. So off to the side. So 1.5 times 1.5 for the 1.5 squared, 5 times 5 is 25, carry the 2, 5, 6, 7. You just did this computation, but that's okay. 225, move the decimal place over twice. 2.25 times 5. Well, that's easy. 5 times 5 is 25, carry the 2, 10, 11, 12, carry the 1, 10, 11. And there are 2 decimal places moved. So this is negative 11.25. This also tells me what 15 times 1.5 is. It'll be that decimal place, but moved back one, because one of these will be moved back one. Plus 22.5. All right, and I guess that means we need to do some subtraction. 22.5 minus 11.25. All right, 15 minus 25 is 25. 22 minus 11 is 11. That could have been easier. And that's not in seconds. That's in meters because it's an output. It's a height. And that is, of course, bigger than 7 meters. So what's the conclusion? Between these sample points, for a time that's between those two, the ball is visible. All right, so how long is this ball visible for each throw? Well, we can compute that. That'll be how long is this time interval? Well, it'll be that time minus this time. All right, that's how you figure out how long something happens. You figure out when it ended, you figure out when it starts, and you take the difference. 15 plus root 85 over 10 minus 15 minus root 85 over 10. Let's compute that. It looks like I have a common denominator already, so that's good. It's all over 10. And how do you subtract fractions? Well, you subtract the numerator, so I guess I should distribute this negative sign into the numerator. So that's 15 plus root 85 minus 15 plus root 85. 15s cancel. 85 stack, so 2 times root 85 over 10 equals root 85 times 2 over 10. 10 is even, so that's root 85 over 5. This 2 cancels that 10 down to a 5. And I guess now that we have this number, I know some things. Root 85, I already said, is a little bit bigger than 9. So this whole thing will be a little bit bigger than 9/5. So that approximation says that this is about 9/5 or 1.8 seconds. Let's do a little bit better by using a machine. Square root of 85 over 5. And we did pretty good. 1.844 is what I'm getting. Cool. All right, so that was fun. So here's the situation. We just solved a quadratic inequality in order to get a measure of how long Dennis Mitchell is at risk of being caught each time he throws the ball. all that today is going to be about is solving quadratic inequalities. Let me give you a tour of the packet. Then we'll do one example, and then I'll stop this recording and we'll get ready to compose the second one. So let's list some examples. So first things first, we'll talk through an example. There's a quadratic function. Let's figure out when it is bigger than or equal to 0. This isn't motivated anymore. Let's just figure out what that is. And the strategy will be the same each time. Solve the equality. This is supposed to be like a slash out for the in. So just the equality. Then either we'll do what we did here. We'll check some sample points to solve the inequality. Or this thing is an upward opening parabola. So we'll be able to just sketch the graph and figure out where the inequality should be true. And then we'll repeat. There will be another one. One that's going to demonstrate some of the weird edge cases that come up. Another one that will demonstrate one of the weird edge cases that can come up. We'll give a flow chart. We'll do some more examples, including some multiple choice. And we will close by pairing this with the idea of domains of square root functions. All right, so here's what I'd like you to do before pulling up the next video. Try to walk through the remaining examples in here. Maybe do it on the notes, maybe just use some scratch paper, and then come back for part 2. Wonderful. So if you're looking at my clock, you will see that it is about time for me to, whatever. It is about time for me to open up the Zoom session for Thursday's class. This is Friday's recording. So I'll see you all real soon. Ciao.